Okay, so we're going to talk about series today. So last class we talked about sequences, which was just a list of numbers, right? A series is a sum of a sequence of numbers. So for example, 1, a half, a third, a fourth is a sequence. It's just a list of numbers. And when you add up all the numbers in that list, 1 plus a half plus a third plus a fourth, we call that a series. So the individual numbers in the series are called the terms. And we're going to want to define the sum of the series. And in this case, it's tricky because we're trying to give meaning to adding infinitely many things. So to give it a definition, we say an infinite series, when you're adding up an infinite number of things, the definition of that thing, the definition of that sum, is the limit of the sequence of partial sums. So the partial sums, S1, S2, here the terms are called S sub n. So my partial sums are just the first term, and then the sum of the first two terms, and then the sum of the first three terms, and then the sum of the first four terms, and then the sum of the first five terms, and that makes its own sequence. That makes its own list of numbers that we can study the way we studied the terms, the sequences from last class. See if that list of numbers approaches the limit. And if it does, we say that the series converges. It has a sum. Okay, so here's the coffee example that I used to introduce limits at the beginning of Calc 1. So if I drink 1 cup of coffee containing 100 milligrams of caffeine every morning, it's known that at the end of 24 hours, about 6% of the caffeine remains in your body. So what quantity is in the body right after I drink my coffee on day 7? So after 1 week. So right after I drink my coffee on day 7, that's 100 milligrams that I just put into my bloodstream. And then I have to add whatever is left over from the coffee I drank the day before, right? So there is 6% of that 100 milligrams still remains. And then I have to add the caffeine that was still in my bloodstream from 2 days ago. So that started with 100 milligrams, and I had 6% was left after 1 day, and after 2 days, 6% of that is left. So you have to multiply by 0.06 squared. Only 6% remains each day for 2 days. And then 3 days ago, I have 100 times 0.06 cubed. And then 4 days ago, 100 times 0.06 to the fourth. And then plus 100 times 0.06 to the fifth, plus 100 times 0.06 to the sixth. And that's 7 days, right? Because this is the beginning of day 7, and then 6, 5, 4, 3, 2, 1. So we want to know how much this is. So I can just add it up. Just type this all in. It's only 7 terms, so it's not too bad to just type this all in. 100 plus 100 times 0.06 plus 100 times 0.06 squared. Thank you. Times 0.06. There we go. Okay. Thank you. Okay, fixed? Okay. 100 times 0.06 to the fourth. 100 times 0.06 to fifth plus 100 times 0.06 to the sixth. I think so. What's bothering you about it? It's the same. You could set it up that way and it would be the same. It would come out the same. Yeah. So this adds up to 106.38 milligrams, which seems reasonable. A little bit more than 100 milligrams, right? You have your 100 milligrams that you just drank, plus what all the leftover that's in your body from the past 6 days. Okay, what happens to the level of caffeine in your body in the long run, though? This is the concern. If you drink 1 cup of coffee every day for infinity, and your body never fully eliminates it, in theory, right? You only eliminate 94% of what's in your body each day. Are you going to OD on caffeine, right? Or does it just level out at some point? It must level out because nobody ODs by drinking 1 cup of coffee every day, right? So we think it's going to sort of stabilize. The amount in your blood is going to stabilize. So let's look at sort of why. Okay. So the caffeine problem is an example of a geometric series. This is a series of the form a plus ax squared plus ax cubed, which means that each term in the series is a constant multiple of the one before, right? A times x is ax, times x again is ax squared, times x again is ax cubed. So that's what makes it geometric. The first term is a, the constant multiplier or the ratio of successive terms is x. So if we have a finite geometric series, like we did when we added up the first 7 days, right? That's a finite geometric series. Every term is the term before it times 0.06. So it's my multiplier is 0.06 and my first term is 100. So if I want to add up a finite geometric series, I'm going to do a little trick here to figure out what it adds up to. So I'm going to say it's got to equal something. Let's call it S for sum, right, of the first n terms of a geometric series. This is going to be a plus ax squared Now I'm going to multiply both sides of this equation by x. And I get x times s sub n is equal to ax plus ax squared plus ax cubed plus, oh, I missed some dots in there. There we go. Okay, and then when I multiply x times x to the n minus 2, what do I get? X to the what? N minus 1, yeah. Because when you have like bases, you add the exponents. N minus 2 plus 1 is n minus 1. And I'm missing an a there. Okay. X to the n minus 1 times x gives me what? X to the n. Add the exponents. N minus 1 plus 1 is n. All right, now I'm going to write the original equation before I multiplied by x underneath here. So I have s sub n equals a plus ax squared plus that's just the original equation. And then I'm going to subtract the 2. That's allowed, right? Legal algebraic move. You have 2 equations, you can subtract them and you get another equivalent equation. So x times s sub n minus s sub n is on the left. And on the right, almost everything drops out. Right? I have ax minus ax squared minus ax squared, ax cubed minus an ax cubed. I have an ax to the n minus 1, ax to the n minus 1. And all I'm left with is a and the ax to the n. I think I meant to subtract it in the other order. Sorry. I meant to have these flipped. So this should be s sub n minus x s sub n. And then I should have an a. So this would be on top, a, and minus ax to the n. Sorry. I guess it wouldn't have mattered. Would have come out the same. I don't know. Do you want me to? Well, I'm trying to figure out what s sub n equals, right? That's the whole point. I want to know what the sum is. So let's factor out an s sub n. And I get 1 minus x over here. And if I factor out an a over here, all right, how do I get s sub n by itself? Divide. Yeah. So s sub n, sum after n days, or n terms in my geometric sequence, is a times 1 minus x to the n over 1 minus x. Can I simplify that? No. The order of operations says I would have to do that x to the n first, so I can't do any canceling. So this is the sum after the first 7 days, first 7 terms of any geometric sequence. So let's say I want to think about my 7 days of caffeine, right? So that sequence was 100 plus 100 times 0.06 plus. Okay. So A, my first term, is 100, and my multiplier is 0.06. And I want to know S sub 7, because I'm adding 7 terms up. So this is going to be 100 times 1 minus 0.06 to the 7th, divided by 1 minus 0.06. And let's just double check that this agrees with what we got when we just added them without a formula. Right, if you only have a few terms, 7 wasn't unreasonable to type it all into the calculator. If you were adding up 100 terms, you might not want to do that. You might use this formula instead. So 0.06 to the 7th, 1 minus that, times 100, divided by 1 minus 0.06 is 0.94, and I get 106.38. Same thing I got when I just added them. So the formula works. The derivation of the formula you are not responsible for. We spent 5 or 10 minutes deriving it, just because I want you to know that math doesn't like poof come out of nowhere. But I'm not going to ask you to prove this unless I put it like as a bonus or something on your test. Okay, so now that we know the sum of a finite series, we can think about an infinite series by letting n go to infinity. Right, so if s sub n, I can add up any finite number of terms in this infinite series that just goes on forever and ever. I can add up any finite number of terms, and it would be a times 1 minus x to the n over 1 minus x. And then I just want to know what happens as I let n go to infinity. So my sum, I'll just use s without an n on it to mean the infinite sum. That is the limit as n goes to infinity of the partial sums. is the limit as n goes to infinity of a times 1 minus x to the n over 1 minus x. All right, what does that equal? What is that limit as n goes to infinity? What the heck is r? I know you do. X to the n would be infinity for what kind of x's? If x were positive and greater than 1, yeah. So if x were a big number, like if x were 10, right, x to the n would go to infinity. This whole thing would diverge, right? The infinite sum would be infinite. So we would say infinite if x is bigger than 1. And what about if x is less than 1? What if that x is a fraction, small number? What happens to x to the n when you raise it to bigger and bigger powers? Teeny number to larger and larger powers. Goes to 0. Yeah. You could just check it if you want. So let's take a small number like 0.1, raise it to the 10. We get a much smaller number, right? 0.1 raised to the 100. It's giving me 0 already because it's so small. Yeah, so this x to the n goes to 0 as n goes to infinity when x is small. So a times 1 minus 0 is a, and 1 minus x doesn't change because there's no n's in there. So this is just a over 1 minus x. So there's two possible sums. It could add up to an infinity, or it could add up to a over 1 minus x. So let's think about the coffee problem. A was 100, x was 0.06. 0.06 is less than 1, so I know that it will converge to s equals 100 over 0.94. That's 1 minus 0.06, which is 106.38. Type that in. (106.38). So after 7 days, we've already reached that limit, that stabilized caffeine level. Okay. All right. I'm going to do a couple of these, or a few of these with you, and then I'll let you do the last couple on your own. Okay, so I want to, for each of the following infinite series, so adding up an infinite number of things, find several partial sums and the whole sum of the infinite series, if it exists. So I have 1 plus a half plus a fourth plus an eighth. So several partial sums. S1 would be 1, right? First partial sum. S2 would be 1 plus a half, or 1 and a half. So the second partial sum is just the first two terms, sum of the first two terms. The third partial sum is the sum of the first three terms, 1 plus a half plus a fourth, which is 1.75. And then the fourth partial sum is the sum of the first four terms, 1 plus a half plus a fourth plus an eighth, which is, I think, 1.825. Maybe one more. S5 is 1 plus a half plus a fourth plus an eighth plus a 16th. 1.825, that's the first four terms. Thank you. 1.825 is the first four terms, and then add the 16th. I think 1.825 might be wrong. 1.875. And then plus a 16th. 1.9375. And let's just do one more. S6, that would be the first 5 terms plus a 32nd. 1.96875. So from the sequence of partial sums, if you just look at this list of numbers, 1, 1.5, 1.75, 1.875, 1.9375, 1.96875, can you make a guess about the limit of the sequence of partial sums? 2. 2. So we would guess, if we knew nothing else, right, that S equals 2. The limit of the sequence of partial sums would be 2. But I actually can calculate it exactly because this is a geometric sequence, right? Is there a number that you can multiply 1 by to make a half? A half, yeah. So if I go times a half, and then a half times a half is a fourth, and a fourth times a half is an eighth, and an eighth times a half is a 16th. So in a geometric sequence where my first term is 1 and my constant multiplier is a half, I know that it will converge because the multiplier is less than 1, and it will converge to a over 1 minus x. 1 over 1 minus a half is 2. Does that make sense? 2 ways to determine if it converges. You can make a sequence of partial sums, and that is, there's a lot of conjecture involved. You have to say, oh, looks like it's converging to 2. If it's geometric, you can say for sure if it converges and what it converges to. In a minute, yeah, we will. Okay, so 1 plus 2 plus 4 plus 8. Let's do a couple partial sums. S1 is 1. S2 is 1 plus 2, the first 2 terms. S3 is the sum of the first 3 terms, which is 7. S4 is 15. From that sequence of partial sums, 1, 3, 7, 15, does it look like we're going to converge to a limit? No, these sums just seem to be getting bigger and bigger and bigger. Is that a geometric series? Yeah, what do you multiply each term by to get to the next? 2. Yeah. So this is geometric, where my first term is 1 and my multiplier is 2. Because that multiplier is bigger than 1, we can say for sure it diverges. Which you can, it's kind of obvious. Add 1 plus 2 plus 4 plus 8. If you just keep adding bigger and bigger numbers, it's going to just blow up to infinity. All right, let's do 3, because that looks a little bit intimidating. 4 and 5 will be similar. Okay. So I want to do 3 together so that, because you haven't seen summation notation for a while. So that says the sum from n equals 1 to infinity of 2 times n minus 1 cubed. So you want to plug in a 1 and then plug in a 2 and then plug in a 3 and add them all up. And a way to do this without making any mistakes is in your calculator to put the formula 2 times x minus 1 cubed, and then I'm just going to use my table. Right? So when I plug a 1 in, I get 0. When I plug in 2, I get 2. Plug in 3, I get 16. When I plug in a 4, I get 54, 128. Diverges. It has to diverge. I'm just adding bigger and bigger numbers together. Yeah. Yeah. The key to something converging is that you have to be, eventually, the things you're adding are so minuscule that it's not going to change the sum enough, right? So if you're just adding bigger and bigger numbers, that's going to diverge. All right, you try 4 and 5. All right, so we have the sum from n equals 0 to infinity of 3 to the n plus 1 times 1/4 to the n. So I plug in my ends starting at 0 because that's what the summation tells me to use first. So when I plug in a 0 for n, I get 3. When I plug in a 1 for n, I get 2.25. And when I plug in a 2 for n, I get 7.5 or 7.5. Yeah. And then if I plug in, yeah, go ahead. Oh yeah, 1.26, yeah. 1.26 something 5625, I think. Yeah. Okay. So the reason I don't want to round them is because when I check to see if it's geometric, I need to see the whole numbers. Okay, so my terms are getting smaller and smaller. Right? So there's a chance this converges because it might be that eventually that the terms get so minuscule that they're not going to push me over some limit. All right, so there's a chance that it converges. I need to know if it's geometric, right? So I need to know, is there some number I can multiply by that will get me from one term to the next? So I just look at the first two terms first, and I say, okay, what would I multiply 3 by to make 2.25? 0.75. How did you figure that out? Divide them. Yep. Yep. So do 2.25 divided by 3. So, oh, 0.75. That's what I'd multiply 3 by to make 2.25. So times 0.75. And then I should double check that 0.75 pattern continues, right? So if I do 3 times 0.75, I get 2.25 times 0.75, I get 1.6875 times 2.25. Oops, what am I doing? Times 0.75 gives me 1.25625. So it does look like this is geometric because I can multiply by the same term every time. So I have my first term is 3, my multiplier is 0.75. Because that multiplier is smaller than 1, I know that this converges to a sum of a over 1 minus x. 3 over 1 minus 0.75 is 12. In the next example, you'll see one. Yeah. So is this okay? So if the terms go to 0, maybe it converges, right? If it's geometric, we can say definitively if it converges or not, and to what. But let's look at this last example. N equals 1 to infinity of 1 over n. So I've got 1 plus a half plus a third plus a fourth plus a fifth. So if I look at some partial sums, I would get S1 is 1, S2 is 1.5, S3 is, I need a calculator, 1.5 plus a third, 1.833. And then plus a fourth, 2.0833. Plus a fifth, 2.283. $2.45. 2.59. Okay, so I'm going to stop here. And I've written out 7 partial sums. Is it at all clear that it's approaching a limit? Not yet. So it doesn't seem to be growing very fast, but I have no conjecture about what it might approach. Maybe 3? I don't know. So now I'm going to check to see if it's geometric. Is there a number you can multiply 1 by to get a half? Yeah, a half, right? But a half times a half, does that give you a third? No, so this is not geometric. So I can't use any of the stuff that we've developed today. The only tool we have right now to tell if this converges is to look at a sequence of partial sums. And right now it's a little unclear. So I was saving showing you how to determine if this converges for next class, but everyone was really mad at me in the last class and they really wanted to know. So I'll show it to you now and just know you don't have to write it down if you don't want to. We'll go over it again on Wednesday. So I'm going to bring back an old concept here. Okay, so there's the graph of 1 over x. If you look at the area underneath this curve from 1 to infinity, what do you know about how much area is there? It diverges, right? That integral diverges. There's infinite area there. Okay. So the integral from 1 to infinity of 1 over x dx is infinite. There's infinite area under that curve. All right, so my sum that I'm interested in, 1 plus a half plus a third plus a fourth. All right, I'm going to use a left-hand Riemann sum to estimate the area under that curve. And each rectangle of that Riemann sum is going to have an area that corresponds to a term in this series. So if I look at this rectangle, right, the height of that rectangle is 1 over 1, the value of the function. So the area of that rectangle is 1. And then I'm going to do another rectangle on the 2 to 3 interval. And the area of that rectangle is 1 by a half, which is a half. And then my next rectangle, its area is a third. And my next one, its area is a fourth. So each rectangle that's estimating the area under that curve corresponds to one of the terms in my infinite series. Now, those rectangles, are those an overestimate or an underestimate for the area under the curve? It's an overestimate. So this sum corresponds to the Riemann sum estimating this area. It's an overestimate of the area, which is infinite. So this sum is bigger than the integral from 1 to infinity of 1 over x dx, which means that it's bigger than infinity, which means that the sum is also infinite. So we would say diverges. So that's an example of a series where the terms go to 0, but it doesn't add up to a finite number. Right? It adds up to infinity. So I'm comparing it to something that I already know is infinite. The area under a curve from 1 to under 1 over x from 1 to infinity, I already know is infinite from like 2 weeks ago, right? And this sum represents these rectangles, which are bigger than that area.
Because it's an overestimate, how does that?
So it's an overestimate, which means that the area in the pink rectangles is bigger than the area under the curve. And the area under the curve is infinite. If you're bigger than something infinite, you have to also be infinite. The only way to be bigger than infinity is to be another infinity. That's why it doesn't converge. It's infinite. That's what diverge means. It's infinite. So this diverges. It grows slowly, but it grows without bound. Okay, so now I'm gonna, as promised, use a calculus method to figure out what these decimals are equal to. We did this algebraically last class. Do it calculusly today. So I'm going to write this as an infinite series. This is 0.19 plus 0.0019 plus 0.000019. 5619 plus. Do you agree that that adds up to 0.19191919? Okay. So, is it geometric? What's my constant multiplier? Just 0.01. Yeah, when I multiply 0.19 by 0.01, that moves the decimal 2 to the left, right? 0.0019 moves the decimal 2 to the left, and I get 0.000019, and then you do it again, right? So my constant multiplier is 0.01. So the sum of this guy is the first term divided by 1 minus the multiplier, which is 0.19 over 0.99, or 19/99. Same thing we got with the algebraic proof. Let's look at 0.9 repeating forever. That's equal to 0.9 plus 0.09 plus 0.009, 0.009. So this is an infinite sum. What's my constant multiplier? 0.1. So my first term is 0.9. My constant multiplier is a tenth. So this is going to add up to first term A over 1 minus the multiplier. 0.9 over 0.9 is 1. It is crazy stuff. All right, last example. Suppose you put $1,000 every year into a savings account that earns 5% a year compounded annually. What is the balance in the savings account right after the nth deposit? All right, so B sub n. So let's say this morning I stopped at the bank and put in my $1,000. So that $1,000 hasn't earned any interest. So it's just in there as the last deposit. And a year ago today, I put in $1,000. So that's been in there for a year, earning 5% interest. So I'll multiply by 0.05. 1.05, because I get to keep 100% of it, plus 5% more. Okay, and 2 years ago today, I put in $1,000, and it's been earning 5% interest for 2 years. And 3 years ago, 0.05 cubed. And I can do this to the n. Is this a geometric sequence? What's my constant multiplier? 1.05. And it's finite, which means I can add it up, right? I have a formula for a finite geometric sequence, even when the multiplier is bigger than 1, right? Because it's finite. You add up a finite number of numbers, you get a finite number, right? So this I actually can calculate to be the first term, 1,000. Oh, maybe I'll write down the formula and then plug in. A times 1 minus x to the n over 1 minus x. So this is 1,000 times 1 minus 1.05 to the n over 1 minus 1.05. And just for fun, let's figure out how much money's in there after 18 years. So this would be 1,000 times 1 minus 1.05 to the 18 divided by 1 minus 1.05. Okay, so if I am careful with the order of operations here, I do 1.05 to the 18th, oops, to the 18th first. I'm going to do 1 minus that. I'm going to multiply that times 1,000. And then I'm going to divide by 1 minus 1.05. Put that in parentheses to make sure it does the denominator first. I'm going to get $28,132.38. Now, what happens if I continue to do this as n goes to infinity, year after year after year after year, from now until forever? What's going to happen to my bank account? It's going to go to infinity. Yeah, it's going to go to infinity. And that's, you would hope that that's how it would work, right? So logically, like knowing what you know about how banks work, your bank account's just going to grow and grow and grow and grow, right? But mathematically, why do you know that it's going to go to infinity? Yeah, I'm adding a big number every year. Yeah. Yep. In terms of using a geometric series formula, the x is bigger than 1. The multiplier is bigger than 1. Yeah. So as n goes to infinity, b sub n goes to infinity. Right? So your bank account balance just grows and grows and grows. All right, so now I have some things for you to try. Geometric series and u. We have one about taking a drug every day. So this is kind of similar to the caffeine example. And then there's another one about winning the lottery.